are from automotive industry or some background? Automotive back. Oh. Any automotive enthusiast? Great. So I am Praveen. I am technical leader, system simulation. So what simulation? Anyone can try a small definition? Okay. Yeah. So just mimicking the real world and trying to create some models. It could be digital, it could be physical, and it could be a combination of both as well sometimes. So Anas is one of my intern. He also contributed to this paper. Thanks to him. So I represent Renault Nissan Tech at MLDS. So most of my presentation, I would like to develop the context first because I know this is the odd man out presentation at MLDS because it's coming from core engineering background. So I'll try to develop the context and just convey how important and how mysterious the problem of battery aging is. And then we'll go into the modeling perspective, what kind of models are traditionally available, and regular machine learning steps like data set, modeling, and finally the best practice of sequence modeling, and we'll conclude. So what's battery? Battery is simply a source of energy, electrical energy. So all our portable devices today, be it your Bluetooth or your mobiles, or your, in fact today it's EV, they're all powered by batteries, so especially lithium-ion batteries today. So what happens in lithium-ion battery or any battery, you have high energy dense or high potential electrode A, from which the electron flows, which is basically the current which powers your devices. So A is nothing but anode and C is cathode, B is the separator between that. So electrical energy stored as a chemical form. That is battery, and it's also source of energy for all our devices. So people might be having some difficulty in conceiving the battery architecture. So I had put like this so that everyone can understand. So the bright slices forms the electrodes and some kind of cheese separator, and you have the electrolyte kind of wedge stuff. So battery is close to us, and literally the energy source. So it comes in all kind of shapes and sizes. We have been playing around with our toys from early childhood. So we have seen all different types of batteries. But what is the solution for EV? It's so important because the specification or the requirement is very huge, or it is also challenging to meet the requirements of the vehicle needs. Typically, over a lifetime, a car would travel 3 lakh kilometers. It should be durable for that long range. So, and today we are talking about long ranges. For example, we would buy a car only if it is having the range of 500 kilometers. So we need a solution which can pack high energy in a small space. So basically, lithium gives a solution because it's light in weight and it can also hold a lot of energy in small space. For example, the comparison between lithium-ion and typical lead-acid battery, it would be like 5x. So same size, but you can pack 5x amount of energy into the lithium-ion battery. So any observation here? What do you see? Yeah, batteries powering cars, but something else. So yeah, China battery. But but today they are the leading powerhouse in terms of, in battery as well as EV. They are giving tough fight for all traditional companies like us. So it's a big challenge. So many companies across globe, they're all trying to do some partnership and develop some ecosystem where they can develop their own batteries. And batteries cause the major cost in a EV, like up to 40%. It's the cost just comes from the battery. So this is a known fact for all of you. The A had few I mean, a couple of A winter, true, right? So only after the inception of the data availability, the compute power, and successful algorithms to train, we have successful models and the booming of deep learning. And today we've gone up to Gen A. So EV is not very far from this. The evolution also goes like that. If you see, 1830 we had EV market. By 1910 we had 30K EVs on road. You know what happened in 1920 which drove the transformation from EV to ICE? Any guess? Not steam engine. Some kind of events happened which catalyzed the transformation. World War. Okay, so the batteries or electric vehicles which were before this, they were all non-rechargeable vehicles as well. So today we all talk about climate change, emission norms are getting stringent every day. We are moving towards BS7 in few years. So the in terms of emission, it's very difficult for OEM to meet the norms. So just a fact, 2024, we have globally sold, not just Renault, globally 17 million EVs were sold. So message is, winter is common for any kind of technology or any kind of revolution and evolution. So simple terminologies. So LFP is a kind of material which go as cathode. Typically anode is graphite, and voltage, capacity, cycles. We typically charge for a while, and then we discharge. As we use, it gets discharged. So this is one cycle: charge 100% and discharge. So this is one cycle. So typically, we all have experience. Initially, our mobiles, when you charge, it will hold for 2 days, sometimes 3 days. But after a year, it will hold only for probably a year and a half. And then slowly drops very drastically. Finally, we will have to charge multiple times a day. So interesting thing is, or challenging part is, batteries age. So initially, let's say 100 is the initial capacity, and then over a period of charge cycles, it ages. So state of health is another important terminology which is needed. Means is, my 20% of capacity has been lost. I cannot, let's say initially your capacity was 100 ampere hour, now only you can push 80. But this threshold, when we reach, it becomes not useful for the EV application. So what it happens is, it is used for the secondary life application, typically for grid usage. So the idea or the problem of battery degradation is complex. So I'll give you a small story. This is the story of 48 identical cells, identical in chemistry, form factor, manufacturing process, and experimental protocol. All were same. So if you look at the initial distribution, the capacity distribution will always have a small distribution, and you will have small tolerance because of the variability in manufacturing. You cannot have all the components as per spec in reality. So after aging, like 1600 cycles, if you look at the dispersion of capacity, if you look at the dispersion, the standard deviation is very high. So any idea what contributed to this? They were all identical, everything like same. So it's a research work done by one of the people. So they attribute this to the manufacturing variation which comes. The electrode separator or the collector. So all these are of the scale like microns, 10 microns, 25 microns. It's hard to keep as per design. Even a small variation, for example, electrolyte, just 1 ml extra, it can drastically change the trajectory of your aging behavior. On top of this, we have many variations specific to users, specific to kind of geographies. We have different temperature. Some drivers could be very aggressive, they'll abuse, and different state of charge when you charge and discharge, and then the kind of breaks you take, and then the cycle number as well as. So all these are increasing the complexity of this problem. So this is this problem is amplified in real world. So again, in an ideal case, you have lithium ions on the cathode. When you charge, it goes to the anode, and then when you discharge, lithium ion shuttles back to the cathode, and electron flows through the external circuit, which powers your car. This is ideal case, but ideal is ideal, right? So it doesn't happen in real world. That too, inside a battery, it's highly complex. You have many kind of degradation mechanisms happening in each constituent of the battery. For example, anode, cathode, separator. So, and these mechanisms or modes, they're all interconnected. So even a small variation at the beginning, it can lead to totally different trajectory. You can see what is the observable thing. So we can observe only the capacity fade, which is nothing but the state of health, reduction in capacity, and then power fade, loss of power. So the degradation is high dimensional problem, just like human ages or human body ages. It's a mystery. We cannot say this is how it degrades. So the key point, all batteries age. Aging is very uncertain. We cannot model it. Traditional modeling, for example, physics-based models, they're going to, for example, in the previous case, what I showed, if you use any physics-based model, all will overlap. They'll have same kind of trajectory for all the cells, but that's not the case. So how are we going to solve this mystery using machine learning? So the business problem, this is a life cycle of any vehicle development. It starts with requirement. We do a lot of system level simulations, component level simulations, and then as the prototype comes, we do a lot of real world testing. We put the vehicle to abuse. For example, in battery case, we do electrical abuse, thermal abuse, and even mechanical abuse, and then check the durability of that. So this is the place where we are spending so much time and effort. Today, cost, effort, they are okay, but not time, because we want to squeeze the product development life cycle in less than 2 years. Because that is also one of the key factor, the time to market. So for an OEM like us, where we validate is at cell level. That is more practical. If it meets the cell level requirements, I'm sure that it's going to meet the module level and the pack level requirements. So the problem is today, the problem which I'm trying to solve is, let's say I have initial some X amount of cycle data, the aging characteristics. Can I forecast into the future? So, for example, in a regular case, we cycle it up to 1500 cycles. It takes almost 1.5 years, 100 cycles in 1 month, typically. So that's a kind of problem I'm trying to solve. So it will get advantage in terms of cost, time, and effort. So time is what is exciting for our management. So I'll try to relate with the LLM. LLMs are advanced than the kind of sequence modeling which I'm showing. But to this crowd, I think this is the way I can introduce the sequence modeling. So in LLMs, what happens? We just try to predict the next word, right? So what happens if the input itself is numeric instead of text? So we do the prediction of the next element in the sequence. So sequence modeling is general term because I'm doing the calendar aging part. So let's keep it kind of flexible or generic. So time series, as per definition, a sequence of data points that occur in successive order. So that's what the definition of. But it's complex. You see, in LLM, it's just univariate. You just have one sequence coming in, and then you just predict one word or the next element. But in real world problems like us, the engineering problems we are trying to solve, we'll have multiple cases or multiple features. And typically we will try to model or forecast many things into the future, not just one variable, but many other things. So it's becoming more and more complex. Now let's get into the actual problem. So this is the data set. So this is an open source data set. I did not use our own, I mean, the Renault's data set because it's highly confidential. We don't want to put the confidential data into public forum like this. And this paper is also getting published, so we are not allowed to put all this confidential data. So we have taken a public data set. So it is LFP. So LFP is becoming more and more popular today, and it's going to be future for few years. But there are a lot of exploration, sodium-ion, and don't know what's going to happen every week. Someone claims that we have identified the best chemistry for batteries. So it consists of 124 cells, 1.1 nominal capacity ampere hour, and then voltage is 3.3, and majorly it is coming from fast charging protocol. So when we do fast charging, we are trying to put more amount of energy or more amount of charge into the battery, but it is going to degrade your battery faster because it increases the stress factor. For example, if you put more amount of charge current into your battery, it's going to degrade faster because of the thermal expansion. Internally, you will have some resistance to flow, so that increases the temperature of the battery. So this is a kind of accelerated aging when it comes to this kind of fast charging. So we need a model which will have some a temporal dependency. So which can model some temporal dependency, or which can have some memory of the past so that it predicts the future. So feed-forward neural network, that's a vanilla architecture. But for this kind of models, RNNs, recurrent neural network, they have some amount of memory. They can remember. So your current output depends on the previous output as well. So this hidden state also has some characteristic or the elements of the previous history. So this is the inception of, I would say, the memory models. After that, we had a lot of inventions of LSTM, long short-term memory, GRU. GRU works for short-term memory, and many other advanced models like temporal CNN. So temporal CNN is nothing but CNN, convolutional neural network, adapted for time series. So instead of grasping the spatial pattern, can we grasp or can we make the model understand the temporal characteristics? Transformer used in LLM, deep Gaussian models. So those are all the models which we tried. So finally we got some good amount of input features, and we wanted to predict next output. So this is a simple pipeline. We'll have the data, kind of time series data. You convert that to trainable format using the sliding window approach. Then you put all the models and see what is the output. And then using the predict and update loop, you kind of forecast into the future. So with the model what we have developed, we can forecast into any number of cycles. So forecasting, when you train, you will get wonderful results like this, the R². But when you do the forecasting, it's going to be difficult because the error keeps on adding, and then it creates a problem because at every when you forecast and then you kind of predict and update, the error is going to accumulate, and finally this is what you reach. So Gardner life cycle, it is to explain any technological evolution. So any product development, it will have similar phases. So this is where actually, I mean, when you fall into the trough of disillusionment, that is where your actual ML work starts. So then you do the hard lifting part. You really get into the problem and try to see what all is scope for improvement. So these are the list of best practice which we used for any kind of time series modeling. So best thing is like sequence decomposition, data augmentation, where you put some noise into your data and then train it so that the model learns or tries to capture the overall trend well. Then model complexity, we need to talk about that. So it also depends on the complexity of your, or the nature of your data. For a less complex data, if you put highly complex model, kind of transformer, or if you put LSTM with too many layers, it's going to give you a hard time. But finally, to be honest, a simple LSTM only worked in this case. So hyperparameter tuning, you can use some of the libraries like KRS-tuner. And all these early stopping, regularization, batch, these are all for making your model more and more generalized. So early stopping is important because overtraining also means overfitting. So when you have limited amount of data, you need to be careful that you are not overtraining. So after doing all these things, this is what we got. So we have initial input like 250 cycle data. From there, how can we forecast into the future up to 2000? This is for another cell up to 1500. So this is what we got. So we also have bounds of plus or minus 10. What we see on the y-axis is normalized capacity. It is not just the capacity. That is why you see the spread of 0 to 1. So the output, what we got was very, very satisfying, because looking at the complexity of the problem, I think this was good. But after this, we continued to work on this and developed the model. Today we have much better results. So I'll just talk about the future work. One is foundation models. So today the battery data is very limited. So what we kind of want to do is, we would like to develop a foundational model, putting all the data available, and then with a good quantum of data, we can have good foundational model from which you can do the kind of fine tuning for and adapt for any kind of chemistry and form factor. The other thing is physics informed. So we are trying to put some amount of physics into the modeling. So typically for ML work, we have the data loss. So how can we put this losses from the physics? For example, we have physics loss, or the governing equation. We convert that to a loss function and then put it for training. So that is one way where you can integrate physics into our models. So it becomes more trustable, and it becomes easy for me to convince my boss. So I know it's the last day and it's already like weekend. So thanks for being here. Thanks for your attention.
Thank you, Praveen. Unfortunately, we won't be able to take questions. We have overshot. I know some of you have questions. Please feel free to get in touch with him outside the hall.
Yeah, I'll wait outside, we can talk.
Yeah.
Hope you had some takeaways today. Thank you.